This mountain looks completely natural, but underneath it, workers have drilled over 40 kilometers of tunnels, poured 180,000 tons of reinforced concrete, installed blast doors weighing 30 tons each, and built a fully functioning military base that can survive a nuclear strike. Here is exactly how they built it every single step. Nothing skipped.
Before a single drill touches the mountain, military geological teams spend up to 2 years studying the rock. They are looking for 4 specific things: granite density above 180 megapascals of compressive strength, minimal underground water flow, no major fault lines within 500 meters, and a mountain mass thick enough to provide at least 100 meters of solid rock cover above the deepest chamber. They drill test boreholes typically 150 millimeters in diameter at 12 different points across the mountain. Each borehole goes down 80 to 120 meters. Sensors are lowered into each hole to measure seismic activity, water table depth, and rock fracture frequency. All of this data is mapped into a 3D geological model of the mountain's interior before construction planning begins. Once the rock passes inspection, engineers calculate the load-bearing capacity of the mountain. Every chamber, every tunnel, every room has a specific ceiling height and width limit based on the rock above it. Exceed that limit, the ceiling collapses. This calculation determines the entire construction layout before excavation starts. Excavation begins with the main access tunnel called the primary adit. This is the largest tunnel in the entire structure. It is typically 8 meters wide, 6 meters tall, and can run anywhere from 200 meters to over 2 kilometers, straight into the mountain. It needs to be this large because this is how all equipment, concrete, steel, and personnel will enter and exit the construction site for years.
The drill head on a tunnel boring machine used for granite rock is fitted with tungsten carbide disc cutters. Each cutter disc is 17 inches in diameter and spins against the rock face under 250 tons of thrust pressure. This pressure cracks the granite along natural fracture lines rather than grinding it down, which is far more efficient and creates less heat. As the boring machine advances, the broken rock called muck falls onto a conveyor belt running through the center of the machine and is carried back out of the tunnel. At peak operation, a single boring machine removes 400 cubic meters of rock per Dalton Y. At that rate, a 500-meter primary tunnel takes approximately 45 days to bore through solid granite. Where the rock quality is lower, softer limestone sections or fractured B-excavation. Method switches from mechanical boring to blaze. Workers drill a precise pattern of 40 to 60 holes into the rock face using pneumatic jackleg drills. Each hole is 38 millimeters in diameter and 3 meters deep. The pattern follows a specific geometry, a center cut surrounded by relief holes, easer holes, and perimeter holes. The holes are loaded with emulsion explosive, a water-resistant compound with the consistency of thick paste. It is pumped into each hole using a loading tube. The center-cut holes receive the highest explosive charge, approximately 1.2 kilograms per hole. The perimeter holes receive the lightest charge, 0.4 kilograms, to keep the tunnel walls clean and prevent over-fracturing the surrounding rock. After all, holes are loaded and wired. The blast is electronically detonated in a precise sequence. Center holes fire first, creating a void. Then relief holes fire milliseconds later, expanding the void. Then perimeter holes fire last, breaking the remaining rock cleanly to the tunnel profile. A single blast advances the tunnel face by 2.5 to 3 meters. Once a section of tunnel is blasted and cleared, structural engineers inspect the exposed rock ceiling and walls before any worker enters. They use a process called rock mass classification, physically tapping the rock with a hammer and listening for hollow sounds that indicate loose or fractured sections. Any unstable rock is mechanically scaled, knocked down with a long scaling bar before the next phase begins. The first structural reinforcement installed is rock bolting. Steel rods, 25 millimeters and 3 to 6 meters long, are drilled into the rock ceiling and walls at pre-CKT-lated angles. Each bolt is inserted into a drilled hole and secured with either a resin cartridge that sets hard around the bolt or a mechanical expansion anchor at the bolt's tip. These bolts stitch the rock mass together from the inside, preventing it from separating along fracture planes. After rock bolting, The tunnel ceiling and upper walls are covered in shotcrete, a high-strength concrete mixture sprayed under high pressure directly onto the rock surface. The nozzle operator stands 1 to 1.5 meters from the surface and applies the shotcrete in layers, first a 50 millimeters base coat. Then, after it cures, a second 50 millimeters structural coat. The final shotcrete shell is 100 millimeters thick and has a compressive strength of 35 megapascals. In sections requiring the highest structural integrity, chamber ceilings, junction points where tunnels intersect, and areas directly below weapon storage rooms, the shotcrete layer is reinforced with welded wire mesh first. Workers attach 150 millimeters by 150 millimeters steel wire mesh panels to the rock bolts, creating a grid across the entire ceiling surface. The shotcrete is then sprayed over and through the mesh, encasing it completely. For the main chambers, the large rooms that will house equipment, barracks, or command facilities, a full cast-in-place concrete arch lining is constructed inside the shotcrete shell. Steel reinforcement bars, called rebar, are bent into arch profiles and assembled into a full rebars, following the chamber's C-curved ceiling shape. These rebar cages are typically 12 millimeters to 20 millimeters. Diameter bars, spaced 150 millimeters apart in both directions. The blast doors are the single most critical construction element in the entire bunker. Each primary blast door is fabricated from 400 millimeters thick rolled homogeneous steel armor plate, the same material grade used in main battle tank hulls. A single door panel is 4 meters tall, 3.5 meters wide, and weighs between 25 and 35 tons. It cannot be fabricated underground. It is manufactured in sections at a surface steel facility, transported to the mountain entrance, and assembled on site. Before the door can be installed, a reinforced door frame called the door surround must be cast into the tunnel wall. Workers excavate a recess in the tunnel walls and floor at the door location. A steel frame built from 200 millimeters by 200 millimeters structural steel box sections is welded together and positioned in the recess. This frame is then connected to the rock bolt system in the walls and fully encased in high-strength concrete, with a minimum of 600 millimeters of concrete behind it on all sides. The door hinges are not conventional hinges. They are pivot pin assemblies, each consisting of a 120 millimeters diameter hardened steel pin, running through sleeve bearings, welded to both the door and the frame. 3 pivot assemblies are used per door, positioned at top, middle, and bottom. Each pivot assembly is rated to carry 15 tons of load. The door's weight is distributed equally across all 3 pivots, so no single point bears the full load. The door sealing system is what makes it blast resistant. When the door closes, a 50 millimeters thick rubber gasket compressed between the door face and the frame creates an airtight seal, blocking over pressure waves from a nearby explosion from entering the tunnel. Additionally, a drop bar locking mechanism, a 100 millimeters diameter solid steel bar that drops vertically into recesses in the floor and ceiling, prevents the door from being forced inward by blast pressure. The locking bar alone can resist 500 tons of lateral force. An underground bunker with no air supply is a tomb. North Korean military bunkers use a dual-circuit ventilation system. One circuit for normal operations, one for NBC nuclear, biological, and chemical contamination scenarios. The construction of this system begins during tunnel excavation because the ventilation shafts must be bored simultaneously with the main tunnels. The primary ventilation shafts are drilled vertically from the mountain surface downward, using rotary drill rigs positioned on the mountaintop. Each shaft is 800 millimeters in diameter and lined with a steel pipe casing, 10 millimeters wall thickness to prevent collapse. The shaft exits at the mountain surface through a disguised rock formation, or beneath dense tree cover to prevent aerial detection. At the base of each vertical shaft, horizontal branch ducts, 600 millimeters diameter galvanized steel pipe, connect the shaft to the main chamber network. These branch ducts are prefabricated in 3-meter sections on the surface then lowered into the tunnel in sections and bolted together underground. Each joint is sealed with a butyl rubber gasket and stainless steel band clamp to maintain airtightness. For NBC contamination events, the ventilation system switches to a sealed filtration mode. At 2 points in the system, just inside the mountain entrance and at the central air handling unit, NBC filter housings are installed. Each housing contains 3 filter stages. First, a pre-filter removing particulates. Second, a HEPA filter, rated to capture particles down to 0.3 microns. Third, an activated carbon filter, absorbing chemical and biological agents. The entire filter change-out procedure can be done in 12 minutes with a 2-person team. A bunker that depends on external power is vulnerable. Every North Korean military bunker has its own independent power generation system. The generators are diesel-powered, typically 2 or 3 units installed in parallel for redundancy. Each generator unit is housed in its own acoustically isolated generator room, a chamber within a chamber, to reduce the acoustic signature that could be detected from the surface by seismic sensors. The generator exhaust cannot simply vent straight out of the mountain the heat signature, and diesel smell would immediately identify the bunker location. The exhaust is routed through a thermal suppression system, a water-cooled heat exchanger that drops the exhaust temperature from 400 degrees Celsius down to below 60 degrees before it exits the mountain through a disguised vent point. The exhaust pipe run from generator to vent exit can be over 300 meters long. Electrical distribution throughout the bunker is run in galvanized steel conduit 25 mm to 50 mm diameter, depending on cable load surface, mounted along the tunnel walls and ceiling using rock bolt ancho. Ours as cable tray supports. The main distribution board is located in a sealed electrical room adjacent to the generator room. From there, sub-circuits run to lighting, equipment outlets, communication systems, and mechanical plant throughout the bunker. Once the structure is sealed, ventilated, and powered, interior construction begins. The rock floor of each chamber is first leveled with a 100 mm concrete screed laid over a damp-proof membrane, a thick polyethylene sheet that prevents ground moisture from wicking up through the floor. The screed is poured and leveled with a screed board, then finished smooth with a steel float trowel. The interior walls are constructed using 100 mm thick precast, concrete panels fabricated in standard sizes on the surface and transported underground. The panels are slotted into steel floor and ceiling channels that are anchored to the rock structure. The joints between panels are filled with a cement-based grout and finished flush. The completed wall surface is then painted with a 2-coat epoxy paint system, a gray primer followed by a light green top coat, standard North Korean military interior finish. Bunk beds in the barracks sections are not brought in as finished furniture. They are fabricated in place from steel angle sections welded to the wall rock anchors. 4-tier bunks are standard, each tier consisting of a welded steel frame supporting a 50 mm thick plywood sleeping platform. Each bunk is 1,900 mm long by 600 mm wide. A full barracks chamber 15 meters long will contain 24 bunks in 3 rows of 8, accommodating 24 soldiers per room. The command room receives the most finished construction. Walls are lined with a secondary steel stud framing system covered in plasterboard, creating a smooth surface for mounting maps, communication equipment, and tactical displays. A raised access floor system, individual 600 mm square floor tiles on adjustable steel pedestals, is installed throughout the command room, allowing power and data cables to run freely beneath the floor and surface anywhere through removable tiles. From geological survey to interior fit-out, a single full-scale North Korean mountain bunker takes between 4 and 7 years to complete, requires between 10,000 and 15,000 workers across all construction phases, and uses an estimated 200,000 tons of concrete and 45,000 tons of structural steel. The result is a facility that can operate completely independently, sealed from the outside world for a minimum of 6 months without resupply. This is not a structure built out of paranoia. This is a structure built by a country that was bombed flat once before. and decided it will never happen again. Every bolt, every pore, every millimeter of steel in these walls is the answer to a single question: how do you build something that cannot be destroyed? This is how.